Hello, my dear student. Welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today, we are going to discuss about the module, the basic properties of nanomaterial part 3 under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to understand the following points. What are potential well at a case of particle in a box, simple harmonic oscillator and parabolic potential, density of state, the state per unit energy range and the size effect, energy level, etc. The exciton, which is electron-hole pair bounded by attractive electrostatic interaction, and quantum confinement. The quantum confinement effect is observed when the size of the particle is too small to be compared to the wavelength of the electron. To understand this effect, we break the word like quantum and confinement. The word confinement means to confine the motion of randomly moving electron to a restricted its motion in a very specific energy level, which is in the discreteness, and quantum reflects the atomic realm of particles. So, as the size of a particle decreases till we reach at a nanoscale, the decrease in confining dimension makes the energy level discrete, and this increase or widen of the band gap, and ultimately the band gap energy also increase. Since the band gap and the wavelength are inversely related to each other, the wavelength decreases with decrease in size, and proof is the emission of blue radiation. Quantum confinement can be observed once the diameter of a material is of same magnitude as the de Broglie wavelength of the electron wave function. When material are this small, their electronic and optical properties deviates substantially from those of the bulk material. A particle behaves as if it was free when the confining dimension is large compared to the wavelength of the particle. During this state, the band gap remains as its original energy due to the continuous energy state. However, as the confining dimensions decreases and reach to a certain limit, typically in the nanoscale range, the energy spectrum becomes discrete. As a result, the band gap becomes size dependent. This ultimately results in a blue shift in the light emission as the size of the particle decreased. Specifically, the effect describes the phenomena resulting from electrons and electron hole being squeezed into a dimension that approaches critical quantum measurement called the exciton Bohr radius. In crucial application, a quantum dot such a small sphere confined in 3 dimensions, a quantum wire confines in 2 dimensions, and a quantum well confined only in 1 dimension. These are also known as 0, 1 and 2-dimensional potential wells respectively. In these cases, they refer to the number of dimensions in which a confined particles can act as free carrier. Here in this module, we have chosen potential well as an example of quantum confinement effect and have calculated its wave function and related energy also. I want to discuss the particle in a box case, which is square well potential. As we know that the size reduction of a system results its quantum confinement. This can be understood in better way by considering the particle in a box problem, square well potential in one dimension. In the present slide, it is explained clearly. Let us consider an one-dimensional potential well extended from x is equal to 0 to x is equal to capital L and having infinite height. Let us consider a particle inside this potential. The potential function for this kind of well may be defined as Vx equal to infinite for x is less or equal to 0 and x is greater or equal to L, and this potential is 0 for 0 less than x less than L. Its simple meaning is that the particle cannot overcome the barrier of the well. Let us write the Schrodinger equation for the particle, which is d2 psi by dx square is equal to minus 2m capital E by h cut square psi or equal to minus k square psi, where psi is the wave function and k is the wave vector, which is given by k equals to under root 2m E by h cut square. The solution of the Schrodinger equation is given by, after solving, one can get psi x is equal to a sin kx plus b cos kx. Let us discuss the quantization and put the boundary condition. Here, the boundary conditions are psi is equal to 0 at x is equal to 0 and psi is equal to 0 at x is equal to L. Using the first boundary condition, where psi is equal to 0 at x is equal to 0, we have b is equal to 0. Thus, the solution will be psi x is equal to a sin kx. And if we use the second boundary condition, where psi is equal to 0 at x is equal to L, we have the solution psi nx is equal to a sin n pi x by L, where a is the constant which can be calculated by using the normalization condition. Using the normalization condition, we have integration minus infinite to plus infinite psi n star x psi n x dx is equal to 1, a square integral 0 to L sin square n pi x by L dx is equal to 1, and therefore we can write that a is equal to under root 2 pi 2 by L. Thus, the expression for the wave function becomes psi nx is equal to under root 2 by L, which is the a value, and sin n pi x by L. The quantized wave number now becomes kn is equal to n pi by L, which we can write under root 2m en by h square. Solving for energy yields, En is equal to n square pi square h square by 2m L square, where n is equal to 1, 2 or 3. Note that the energy depends on integral value of n. Hence, the energy is quantized and non-zero. The special case for n is equal to 1 is called the ground state, where n1 is equal to pi square h square 2 pi 2ml square. Let us discuss this quantized energy. In this slide, we have plotted the energy levels, wave function, and also the probability as a function of n. From the figure, it can be said that for the different value of n, we have different energy levels. Also, the spacing between the energy levels increases with increase in the value of n. Similarly, for different value of n, the wave functions for the electron is shown in the figure. The probability density is defined as the square of mod of psi, which is p psi is equal to mod of square of psi. The plot for the probability density for the different values of n has been shown figure 2. Consider the second order term of a Taylor expansion of the potential function. Vx is equal to half V2 x minus x0 square. Substituting this into Schrodinger equation, the equation can be turned out like d2 psi by dx square is equal to minus 2m by h square e minus kx square by 2 psi are equal to in bracket minus 2me by h square plus mkx square h square psi. Let alpha square is equal to mk by h square and beta is equal to 2me by h square, which yields d2 psi by dx square is equal to alpha square x square minus beta psi. The parabolic potential well case. Simple harmonic oscillator potential, also known as parabolic potential. If we solve the Schrodinger equation corresponding to this potential, we have En is equal to n plus half h cut under root k by m equal to n plus half h cut omega. If we put the different value of n, we will get the different energy levels. Here, the energy levels are equidistant. For example, the gap between any two energy levels is same and is equal to h nu. The schematic representation of energy levels have been shown in the figure, and other figures shows the different possible wave function for such kind of potential. Here, a term called 0-point energy is defined, which is obtained by putting n is equal to 0. I want to discuss the density of state, the state per unit energy range. The density of state is essentially known as DOS, is the number of different states at a particular energy level that electrons are allowed to occupy. For example, the number of electron state per unit volume per unit energy. Bulk properties such as specific heat, paramagnetic susceptibility, and other transport phenomena of conductive solid depends on this function. Before going for the semiconductor statistics, one should know about their density of state. For 3D nanostructure, density of state is directly proportional to the square root of energy. For two-dimensional nanostructure, it is independent of energy, and for one-dimensional nanostructure, it is inversely proportional to the square root of energy, and for 0D nanostructure, it is a delta function. Where I want to discuss the size effect, energy levels and density of state. How energy is quantized when the dimension of a system is reduced. When we consider a semiconductor in bulk form, it have fully filled valence band and partially filled conduction band, separated by a finite band gap. In this case, Fermi level lies in between the valence band and conduction band. When the dimension of the system is reduced to nano form, it possesses energy level in discrete form. When the size is reduced up to atomic level, in place of conduction band and valence band, lowest occupied molecular orbitals known as LUMO and highest occupied molecular orbitals known as HOMO are considered. Right side figure shows the variation of density of state which we have already discussed in previous slide, from where we conclude that the size reduction lead to the tuning, the band gap and also the discrete energy level. The exciton, which is electron-hole pair bounded by attractive electrostatic interaction in case of hydrogen atom. An exciton is a bound state of an electron and an electron hole which are attracted to each other by electrostatic coulombic force. It is an electrically neutral quasi-particle that exists in insulator, semiconductor and in some liquids. The excitons is regarded as an elementary excitation of condensed matter that can transport energy without transporting net electric charge. An exciton can form when a photon is absorbed by a semiconductor. This excites an electron from the valence band into the conduction band. In turn, this level behind a positively charged electron hole, an abstraction from location from which an electron was moved. The electron in the conduction band is then effectively attracted to this localized hole by the repulsive Coulomb forces from large number of electrons surrounding the hole and excited electron. This attraction provides a stabilizing energy balance. Consequently, the exciton has slightly less energy than the unbound electron and hole. The wave function of the bound state is said to be hydrogenic, an exotic atom state akin to that of a hydrogen atom. However, the binding energy is much smaller and the particle size much larger than the hydrogen atom. This is because of both the screening of the Coulomb force by other electron in semiconductor. For example, its dielectric constant and the small effective masses of the excited electron and hole. The recombination of the electron and hole, the decay of the exciton is limited by resonance stabilization due to the overlap of the electron and hole wave function, resulting in an extended lifetime for the exciton. The electron and hole may have either parallel or anti-parallel spin. The spin are coupled by the exchange interaction, giving rise to exciton fine structure. In periodic lattice, the properties of an exciton show momentum k-vector dependence. Binding energy of an exciton is given by the formula E is equal to m e to the power 4 by 2e h cut square n square, and the radius is given by r equal to n square e h cut square by m e square. 1 by m is equal to 1 by me plus 1 by mh. Here m is the reduced mass, me is the mass of the electron, and mh is the mass of hole. Here I have listed the binding energy and radius of few semiconductor nanocrystal possessing excitons. For example, in case of silicon, the energy is 14.7 MeV and radius is 4.3 nanometer. In case of germanium, it is 3.8 to 4.1 and radius is 11.5 nanometer. Gallium arsenide, this energy is 4.2 MeV and radius is 12.4 nanometer. Where quantum confines will be discussed in detail. We have depicted the pictorial representation of the excitonic radius. If there is the formation of exciton in a crystal, then the energy calculated by considering the particle in a box is modified and is given by the formula Er is equal to h square pi square by 2m r square minus 1.8 e square 2e into r, where r is the size of the nanoparticle and small r is the radius of exciton. From this expression, we can get the condition of a strong as well as weak confinement. If capital R is less than small r, then the quantum confinement is considered as a strong in nature. In case of strong confinement, electrons and holes both are confined and the energy gap varies as the inverse of the square of capital R. This depends upon the size of the crystal and the size of exciton n in that particular crystals. For example, if the size of silicon is less than 4.3 nanometer, then it is said to be strong confinement. Similarly, for germanium, it is 11.5 nanometer, and for gallium arsenide, it is 12.4 nanometer, which I have discussed earlier. While if R is greater than small r, the confinement is called weak. In this case, second term of the energy expression is dominating. This term is referred as Coulombic term. In this case, electron and hole are not confined while exciton shows the confinement. So student, let us now summarize what we have learned in this module. For a particle confined within an infinite potential well, Schrodinger equation is given by d2 psi by dx square equal to minus 2meh square psi equal to minus k square psi, where k is equal to under root 2m e by h square. The corresponding wave function and energies are respectively written as psi nx is equal to under root 2 by L sine n pi x by L, and the energy is En is equal to n square pi square h square by 2m L square, where n is the natural number. Examples of parabolic potential is simple harmonic oscillator problem, which we have learned in this module. The energy of a harmonic oscillator is given by En is equal to n plus half h under root k by m, which is equal to n plus half h cut omega. Excitation are the bound state of an electron and hole. We have also learned that if the size of the excitation radius is comparable to the size of the particle, it is said to be strongly confined, otherwise there is a weak confinement. Thank you.